Welcome to Science is Your World. I'm Peter Shacklock, and I'll be the host for this show. Today in the studio, we have as our guest Mr. Frank Cruikshank, and he's the Regional Groundwater Hydrologist for the Water Resources Directorate for Environment Canada. That's quite a mouthful.
Yes, it is.
Yeah, welcome to the show there, Frank.
Thank you.
Okay. Now, our topic is going to be aquifer thermal energy storage. And that's about all I'm going to say about this for now, because I'm going to learn as we go along here, but maybe, Frank, you can explain exactly what aquifer thermal energy storage is.
Yes, aquifer thermal energy storage, we call it ATES in the business, or ATES. And it involves the storage of excess heat or chill underground and in water-bearing rocks or strata called aquifers. And aquifers are where people get their groundwater supplies from. Right. So the word aquifer means, it's a Latin term. Aqua is water and fer to bear, so it's basically it's water-bearing rocks.
Mm-hmm. And okay. Thermal energy storage is just, we're going to be using it to...
What we do is we take excess heat that would otherwise be wasted, for example, and we store that underground for use later on when it's cold out. Or conversely, we can take the chill from winter and store some of that in the ground for air conditioning in the summer. And cost savings in terms of energy are, you can get as much as 50%, no problem.
Really?
Yes, and it can be done at a commercial level and scale. And right now with Environment Canada and many other partners, I must say, we're developing guidelines and standards and developing systems so that we can manage the environment properly and so that there's no negative impacts and only positive benefits for society.
Great. Okay. You have a number of slides you brought with us?
Yes, I do. I'll start off with the first slide, of course, and it says ATES, A-T-E-S, as I said earlier, and I'll just move along quickly. The second slide, that came from a friend of mine who he's from Sweden, and in Sweden they've done many, many different types of thermal energy storage, far more than what we've done here in Canada. And what you can see is on the far right-hand side with the red caverns underground, storage of heat in caverns or even chill. And you can see vertical tubes and horizontal tubes next to those caverns just above them. And those are called closed loops, and they can store, they actually extract heat and chill from the ground more than storage. At least that's how they're being employed now. You can see to the far left where there's a blue for the water body. You can use, of course, water from surface water to cool a plant or something like this. And in the very middle there's a what we call an esker in geological terms. It's just a sinuous body of sand and gravel that's in this case saturated with water. And the esker, the water that's in it is groundwater, and it is an aquifer. Although all aquifers aren't eskers, they can also be bedrock.
Oh, really? So you can actually have bedrock as a heat storage system the same as this?
That's right.
Just must be a larger area, isn't it?
That's right. Yeah. And they found in Europe, mostly where a lot of this work is going on, that these harder rocks like the granites that we find around here, or the slates and quartzites that we have beneath the city of Halifax and Dartmouth, it's relatively expensive to store heat in those types of rocks. So we look for rocks that have water in them. Yeah. Okay? So the water acts as a medium to pass the energy to and from the aquifer.
Right.
Now, what I'm focusing on, being a regional groundwater hydrologist, is groundwater. And it's very important that we manage our groundwater resources, because groundwater, well, I'll put it to you this way, over 90% of all available fresh water is underground.
Really?
Yes, over 90%. So if you exclude the glaciers, which is not really available to us, then fresh water, most of it's underground. And so when a river flows during a drought, it's coming from groundwater. Okay? Yeah. That's very important to realize how much water there is underground. So what's out of sight is often out of mind, and my job is to make sure that it's not out of mind, that we keep it in mind. Okay? And I'll let you know how this process works. We want to store energy because it's more environmentally sound to do that in the long term. It can reduce global warming, for example, and of course reduce by reducing the amount of energy you use, of course, you're reducing air pollutants and these types of things, okay? Yeah. And it also is great for generating wealth for the companies that may use the technology, because they save a lot of money in their power bills. Yeah. And also the power companies save, depending on which province you're in or which region you're in, because they tend to reduce what's called peak load. So, in other words, if we use less electricity, then they have to build less plants to meet the peak load, and that can help stabilize electrical costs. Okay. Now this slide shows it's actual data from New Brunswick from many years ago. However, it stands true today, and you'll see a more or less horizontal line, it represents the temperature of groundwater, and groundwater is usually below. This is below the frost level. Okay. Yeah. And so groundwater sits in those aquifers, and this is the temperature throughout the year. Now you'll notice this other line that goes above and then below the horizontal line, and that line is the temperature of the air through 1 year. So you'll see that the temperature of air, as everyone knows, goes up and down according to the season. Yeah. But the groundwater temperature stays stable, and it's the stable temperature and the stable condition that allows us to use the aquifers as heat stores and chill stores. Okay? Mm-hmm. Now, we can actually use this water directly for heating or cooling, and we don't have to store energy. And it's because in the summer, when it's hot, the groundwater is cool relative to the outdoors. Okay? Yeah. And conversely for the winter. Mm-hmm. I'll move on. This is a project that was started about 10 years ago in Scarborough, Ontario by Public Works Canada. And it's in a building. It's the Atmospheric Environmental Services, actually, for Environment Canada. What this is Scarborough Centre is the name of the building, and I should say Dr. Morawski of Public Works at that time was, if you will, working out some of the bugs to the technology, and he was able to set up this project, and I must say it's working very, very well. So you'll see the building. What we're doing here is you have these layers of rock, and the blue represents the aquifer in this case. So above that may be sand, maybe clay material or something like this. But the aquifer itself will be something like a sandstone or some porous rock. And you'll notice that there's a red area and a well leading down to it. Well, that's where what's happening in this case is cool groundwater is being brought up to cool the building. Okay, yeah. Let's assume it's maybe 8 degrees Celsius. Yeah. And in the summer it might be 20 or 30 degrees Celsius. And in these buildings particularly, there's a lot of computers, so it's very hot and a lot of people. So cool groundwater is brought up to cool the building, and then that cool groundwater heats up. There's no exchange of water, but just heat to the groundwater. And then that cool groundwater, as it warms up, is put back into the aquifer in a different location. And you see the red is the warm groundwater relative to the background. And that warm groundwater will be brought back up in the winter to heat the building. And cooler groundwater will go back down into the aquifer in this second well. Okay?
I see.
So you end up having a background temperature of maybe 8 degrees, and then in your cool wells it may be 5 degrees Celsius, and then in your warm wells it may be 12, 18, or 20. It could be many different temperatures depending on the building.
Mm-hmm. How far apart can those two different temperatures be?
Well, that's the most important part. Between 50 and 300 meters would be a rule of thumb. And what happens is that in each case we determine that based on the hydraulic properties of these rocks, okay, the water flow properties. Yeah. All right? It's very important in most cases not to allow the stores to mix together, at least not greatly. Mm-hmm. Okay? However, by doing aquifer storage, what you're really doing is conserving. I mean, a certain amount of energy is lost. The energy is lost, there's no doubt about it. But enough is saved such that, and as far as Environment Canada is concerned, we want to balance the thermal regime in the aquifer, okay? Right. So thermal balancing of the aquifer. We also want to do water conservation by making sure water goes back into the aquifer, okay, instead of wasting it to the surface. Right. And of course, we also want to do chemical balancing of the aquifer because there's chemistry involved here. Mm-hmm. Maybe I should move on to the next one. Okay. What I want to do in Canada, and we're starting this with Sussex, New Brunswick, is develop community-based thermal energy storage. In other words, what I'm saying is instead of doing one building at a time and then trying to figure out, I'll back up and say it's better to plan for a community than it is to do one building at a time. because then you in one fell swoop you can determine a lot about the geology, hydraulic properties, where to put the systems, where not to put them, etc. Both based on the buildings themselves, the community's needs, and the hydrogeologic regime. Okay?
You got a much larger area to work with.
That's right. There's there's efficiencies in scale, you see. And then the project managers don't do one project and leave. Rather, they're working with the community and identifying good projects and trying to amalgamate them, because one building's waste heat may be another building's source of energy. Okay?
Yeah, yeah.
So in this case, you'll see these buildings are linked, and it shows that there's houses and commercial buildings and the like, and institutional buildings. And the thermal regime, you have warm well and a cold well, and what you do is try to balance the temperatures between those two so that they don't mix too much. Right? So maybe I'll move on.
Okay.
Okay. I want you to know, too, that we can store energy from power plants, from solar units, from commercial enterprises. It doesn't really matter. It's, for example, one of the projects I would like to get going in the future is storing heat from a thermal generating plant. And there's some new ones being built in New Brunswick, and I've been discussing this matter with some people there. So what would happen is, we don't suggest that a plant be built, but if one is being built and it's been approved environmentally, etc., then you should know that most power plants waste 70% of their energy in the form of heat. And it's usually discharged as warm water from the plant, and it goes into our environment. So this, of course, is one of the causes for global warming. And if we can store that energy in aquifers, then at the very least we'll reduce the effect of global warming. So with proper hydrogeologic studies, we can do this. All right. And now, if there is a need to use the heat in greenhouses and apartment complexes and the like, we can do that too. You see, because we're building a store of heat. Okay. And the groundwater is used to cool the plants. I'll move on to the next one. This was a plant I visited in Sweden last year. Now, this is really low-grade geothermal. However, it does show you what a plant would look like, the layout of a plant, okay? And in this case, my colleagues there, quite by chance, looking at some seismic surveys, determined that at about 700 meters below surface, there was a sand layer, and that sand layer was actually an aquifer. It had a lot of water in it. And so they they persuaded some people to do a drilling program. And they drilled and they found this water. Now, that meant that in this particular city, the city of Lund in Sweden, they actually have a district heating system, okay, where they use coal, oil, and other products to make heat and send it through a district heating system. And there's 2,500 buildings on the system.
Oh, really?
Yeah. Now, I say residences in this slide, but it's really buildings. It's the same as maybe downtown Dartmouth, or quite larger, actually, larger than that, or Bedford. And so what they do is preheat the boiler water with their groundwater. So the groundwater comes up, it goes at 20 degrees Celsius approximately, and it goes through a heat exchanger that they designed. It looks somewhat like a very large jet engine in this case. And they take heat from that groundwater and put it into their boiler water before the boiler water is actually boiled, okay? Because it preheats it, and it's less heating required, and then that just goes through the network, and when it comes back cool, the cool water is exchanged and put back down into these other wells, which are shown in blue. So I was showing earlier one or two wells, but what the real situation is, several wells and two small well fields like this. Now, what's really interesting is that this slide shows in this orangey color shows how much oil they were using in the past, okay? And then the next pie in the orange shows how much the oil they're using now, and the rest of the energy in red and in yellow is what's being produced by this thermal storage process.
Really? Yeah, it's really...
Yes, so it's something like, they're replacing something like 35,000 cubic meters of oil per year in this one plant. And I can only say that they can't help. This is a non-profit company. It's a utility run by the community, and they cannot help but make $10 million a year on this project.
actually making money.
Yes.
Oh.
So they have lots of money for research, monitoring, and the types of things we like to see in these projects, right?
Yeah.
And of course, in Europe, energy supplies are a critical matter. They're far more sensitive to it than we are. So it's nice to have an energy mix like this.
Right. The original source was quite a lot of oil, but now they've.
Yes, that's right.
I think it's their least source.
Yes.
It is.
And you can see that the energy mix has changed over the years too. In other words, they try to get as much gas and oil from as nearby as possible.
How long has this been running over there?
I'm not sure exactly. There are dates on there that I can't see from here, but it's been 5 or 6 years anyways.
So it's well established and running?
Yes, it is.
Yeah, good.
Now, what I'm trying to do here is, in Atlantic Canada, is develop model communities. It's very important. I'm working with the International Energy Agency on this as well. It's what we will be calling an implementing agreement. They have lots of research agreements, and they're given a name called an annex, Annex 1, 2, 3, or 4, like this. Well, this will be called Annex 8, and it'll be an implementing agreement. It's to take all the technology that we've developed over the past, well, it's been about 30 years since the technology started, but it's really only been about 10 years that great progress has been made. And the trick is to take the technology and put it all to use as opposed to leaving any of it on the shelf. So we're going to call it an implementing agreement. And one idea that I've been putting through and have written on is the community-based process, right? And so we're starting that process in Sussex, New Brunswick.
This is going to be a new...
You bet.
No, it's new to the whole system, but I mean a new development that's going on?
Yes, I'll explain that in just a moment. It's what we're going to do is convert their regional hospital over to thermal energy storage. And that's quite significant in that hospitals need very secure energy supplies. And a successful project of this type would show that the technology can be used in even the most sensitive of buildings. In other words, a hospital. Also, it's very important we're working with New Brunswick Environment to manage groundwater. So at the same time we're doing this work on one side of the river, on the other side of the river, the town of Sussex and the province of New Brunswick and others are working to develop groundwater protection zones. Okay, so I want to make sure that thermal energy storage can be worked into these processes. Okay, this slide shows shows the town of Sussex somewhat, and the green shows sand and gravel deposits, and the whitish areas are what we would call till deposits. That is clay type materials that don't normally yield water to wells. Okay, most of the water for the town of Sussex comes from the green deposits of sand and gravel. Okay, and what I have here are I'm going to show 3 slides after this slide that shows a cross-section, what it would look like below ground, based on some drilled wells. That's lower left, and the upper central part is ground-penetrating radar, and to the far right, the blue, it's a landfill site that's being decommissioned. However, it's fairly close to our project, and I want to emphasize that the first thing you do in a screening is determine if there are any potential sources of pollution, and make sure you deal with that first. It's the most important thing you can do. Okay, not to hide from it, but rather to work with it and deal with it. So the next slide is this cross section, and what it shows is the green is what we call an upper aquifer. It's not used by the town. It's sand and gravel, and then below that is a clay or bouldery till, which acts somewhat as an impervious layer. It somewhat protects the lower aquifer, which is sand and gravel. Now this diagram, these are all schematics, so they're not drawn to scale for anyone who may be a geologist, for example.
Okay.
It's done just to give you an idea of the situation. And below that is bedrock. So these wells give you an indication of where the town gets their water supply from. Okay?
The actual source would probably be miles and miles away from some hill or mountain.
You're right. Yeah. The recharge area would have to be defined, to be defined, I should say. Okay, that's correct. Groundwater moves from high to low energy areas. And in our business, what goes down must come up. That's the way we look at it.
Okay.
Yeah. Anything that goes in the ground usually appears somewhere else and within the flow regime, because Okay, from the high energy to the low, it appears. This, I hope this is visible on your screen, because it's it just gives you an indication of some of the technology we use. But without drilling and in a different location, we were able to determine that using ground-penetrating radar, that there is another sand and gravel deposit at another location in the town, and that the V shape to the far right is a buried paleo or ancient river channel that is buried. You can't see it except through the radar. Okay.
And there's still water in that.
In this aquifer, there's water, yes. And where the pictures kind of stop and becomes fuzzier, that's that clay barrier that you saw in the drill logs.
Yeah.
Okay. And if this radar could go through that, it would probably pick up the sand and gravel below that. Unfortunately, the signal's attenuated in clay. Okay. So it can tell you where buried channels are, sand and gravel, before you drill. It's just some of the technology we use. I did this block diagram to show your audience the juxtaposition of this particular landfill site. You'll see it is placed in sand and gravel deposit, okay? The green. However, below that is this till deposit, which is relatively impervious, and then a silt deposit. And the little bit of white in the diagram is where there's no data. So the first thing to do is find out what is the situation below the landfill, right? And then determine flow directions and the like to make sure that doesn't affect your project adversely. Now, all of this type of data would be put together in probably a geographic information system and cataloged, and you can actually manipulate the data and make calculations about maybe groundwater flow and these types of things. This diagram is another block diagram, but it's somewhat different than the other ones. It shows the bedrock geology. And you'll notice I have a picture there with the yellow arrow pointing down, and that would show where the hospital facility is located in that town, okay? I couldn't quite fit it on there at the time, so I put it in as an arrow. Now, you'll notice that there's layers of bedrock, and these layers are folded and faulted, actually. And what I would do, and what we're doing now, is doing some drilling in that area, determining which is the best aquifer to store our heat and cold. Okay?
Yeah. The light blue, can you reiterate what that was?
The light blue is what they call the Weldon Formation. And then the other formations are Hillsborough and there's Macomber. And each of these formations, what's interesting about Sussex, because some of my research money is coming from the Panel for Energy Research and Development, okay? Also, you'll see later on where it's coming from, but they want us to look into some water treatment technologies that have been developed just for ATES. It's been done in Europe, and okay? And this geology is so diverse that it has many different kinds of chemistry. And this is a plan view of the same thing, all right, with the river going through. Here it shows the industrial park and the hospital complex, and you'll see it's next to the industrial park, and the work we did in orange is where we had the ground radar. And we're staying away now from the groundwater supply for the community because we really shouldn't be working there at this time. And this gives you an idea of what the hospital looks like, which is in brown, and the senior citizens and New Brunswick Power District office. And some of these buildings are already on earth energy at the present time, but not thermal energy storage. They're not storing energy.
So they're using like a heat pump system.
That's exactly what they're doing.
Bringing water up, and they're putting the water back down again?
Yes, they are.
Okay.
So
actually,
they're balancing that component.
Yeah.
Now we want to balance the heat, and we'll do that with those complexes too, those buildings, I should say. So this shows 3 of the buildings that are using groundwater energy, and the point is that the chemistries there show that they're all in different formations or likely influenced by different formations, and those colored diagrams I showed earlier shows that the contacts between those rocks are very close. And these are some of the people that are involved. The upper level is that it's Environment Canada, and we're chairing this steering committee, the Canadian Electrical Association, the New Brunswick Department of the Environment in the town of Sussex. And on the far right it shows that we have people involved all across the country, from Public Works and our research people, and some local talent that we're giving this technology to. And then in the center, we get a lot of advice from the International Energy Agency. Okay. here, once again, this is the same idea. What we want to do is develop guidelines. And on the far left, it shows that we have to use some computer technology. And then, of course, we have to find ways to store the data that we gather properly and develop these guidelines. And then on the far right, this is development of a model community, because you really need an example. Otherwise, you're just going to be an armchair type environmentalist or hydrogeologist or whatever it may be. Okay, and you can see there's a lot of participants. It takes a lot of people to make something like this happen. So ultimately, we want to make thermal energy storage a something that anyone here in the country can use safely and have guidelines to follow. Okay, and all based on a community model. So the objectives are to save energy, to manage groundwater, and develop codes of practice such that our department or other environment departments can look at a project squarely and determine if it would be environmentally sound or not. Okay, and also whether or not people are going to save energy. Well, those protocols would be developed too. So just quickly, I'll say that these are the steps that you use to work on a project. You have to do your preliminary work and then your aquifer characterization and some modeling using computer models. And that's what the International Energy Agency has developed, a lot of different models for chemistry and groundwater flow and temperature exchange. And then we would instrument, because it's important to do monitoring so that you can determine how the facility is functioning. So this is subsurface and in the building. So you connect the aquifer with the building, so they operate as one. And then, of course, there's always reporting and debriefing like we're doing now. All right. So once again, demand-side management for the utilities, the quantity of savings in energy for the buildings themselves and how much money they can save, and then, of course, the environmental impact assessment type process where we can manage our aquifers and water and still make groundwater a value-added product. And that concludes at least the slides.
Okay. We only have about 1 minute left, so I just have one question about the chance of introducing any pollutants or any kind of problem by bringing the water up to the surface and putting it back down.
Well, that's the first question you have to ask yourself, okay?
Yeah.
So the first thing we do is determine what the water quality is, and that's why we do all of the work, the background work, to determine where pollution sources may be. So before any water goes back in, it would be evaluated. However, what's been happening is that basically that has not been happening in this country. People have not been evaluating water quality. They haven't gone out and done site surveys. So they've been putting water back in where maybe they shouldn't be.
Exactly.
So far, not too bad, but there have been some problems, and we'd like to alleviate those.
Okay. That's why Environment Canada is involved.
You bet.
Okay. Okay, I'd like to thank you for coming. Our guest today has been Frank Cruikshank, and he's the regional groundwater hydrologist with Environment Canada. And we've been talking about aquifer, thermal energy storage. And I'd like to thank you for watching the show, Science is Your World, and why don't you tune us in again next week. Thank you.